Hello, everybody. Good morning to those who celebrate, and a happy afternoon to those who are watching this in a few hours. Today, we are continuing our journey through Vakil, the Rising Sea, in this kind of informal way. So, last time we ended with fibered products and then um, basically pullback diagrams. And so we said that fiber products were an example of pullback diagrams, where the fiber product through z of x and y is the pullback of z. Um, so today we're going to try and get through Yoneda's lemma. I really don't know if I'm saying that right. This is kind of the danger of self-studying, right? Is sometimes you don't know the names of things or how to pronounce them. But yeah, we're gonna try and get through Yoneda's lemma. That's like 3 pages. I think that's pretty good progress for 2 hours. Um, so yeah. Uh, let's see. So our first thing is an exercise on fiber products of sets. So I'm just gonna go ahead and copy this commutative diagram. Um, and then that's what we're gonna start our new notes with. Wow, lecture 10. We're getting into this. This is exciting. So there we go. And then we're just calling this the fibered product diagram. Hold on, I have to blow my nose again. I'm battling a bit of a sickness. All right. So, as an exercise, show that for the category of sets, goodness gracious, the fibered product through z of x and y is equal to x comma y and x prog y. Wow, that such that alpha of x is equal to beta of y. Associated into this diagram here. And I need to blow my nose again. Okay, sorry about that. And then the subtext is that more precisely show that the right-hand side equipped with the evident maps to x and y satisfies the universal property of the fibered product. And so basically, we want to show that we can either do set containment or we can show that the right side is the unique excuse me, as the unique factorization um, through X fibered product Y. Um, so meaning we want to set, I guess, I'm guessing that our diagram should look like, that's Y canonically, that's X, that's Z, and then this is beta, this is alpha. I think that this is what they're asking us to show, is that X product Y factors through the fibered product. Well, let's start by examining the structure of Z, right? So in Z, points are identified by essentially alpha of X equals beta of Y. Being the same thing. And so, do we have anything specific about alpha and beta? So we have in the universal property of fiber products, we're given pi x and pi y is an object with morphisms, the pi's, where the compositions of alpha and beta agree such that any given object W maps to X and Y through the fibered product. Yeah. I mean, this is just kind of like I think an intuition thing, right? Like this is the objects in Z have to have this. And then the fibered product is all of the pairs in the actual product which factor this way, and then that is a unique factorization. I'm not really sure how to show that. Like, it's just kind of proof by definition. Does that make sense?
Yeah, it does.
Or can you think of a way to like more rigorously show? Like, obviously we can say let x naught and y naught in x comma y. Um, and then say, well, if alpha of x equals beta of y, then its image in Z is the same thing, and so it traces back to the fibered product. Actually, this is probably what we should do. Okay, so
Yeah.
so formal. Let x naught comma y naught in x product y with, and let's just call these f1 and f2. With f1 composed with beta of y naught equal alpha composed with f2 of x naught. Oh. This was not meant to go all the way to Z. There we go. Now the diagram is correct. For those watching the recording, it's 8 a.m. Give me a break. And so then we have that this composition works. But then the way that we set up pi x and pi y is basically that that beta composed with pi x. Nope. Composed with pi y. Nope. Oh my gosh, I keep picking the wrong thing. There we go. Is equal to alpha composed with pi x. X naught. Um, by definition, and so basically we can factor. So beta circ f1 is equal to, and we'll call this thing, we'll call the factorization phi, is equal to, oh no, let me get this off. Phi circ beta circ pi y, and then alpha circ f2 is equal to phi circ alpha circ pi x. And I think with a few extra steps that that kind of tie that together, it should work. So does this make sense about like how this is explaining what the fibered product does? So the fibered product is all of the things which have maps that agree in Z.
Yeah, that makes perfect sense, actually.
Yeah. And then this is the same notion as the pullback, right? So the pullback of Z in any diagram is going to be the thing that like has two maps going into it that agree in X and Y.
Yeah. No, that makes sense.
I'm going to blow my nose real quick while the Apple Pencil charges.
Yes.
Okay. Yeah, I forgot to charge my iPad over the past few days.
Oh.
Yeah. So the next exercise is to say, okay, if X is a topological space, show that the fibered products always exist in the category of open sets by describing what a fibered product is. And what that really means is that fibered products in the category of topologies are intersections of open sets.
Oh, okay. Could you repeat that?
The fibered products in the category of topologies are intersections of open sets.
Okay, thank you.
Yeah, and we're going to prove that in just a second. Um, yeah. So the exercise is really to figure that out, but I think it's kind of easier to say, hey, this thing is true. Prove it. uh, once this gets up to like 25, we can. Yeah. Any day now. Yeah. So normally this is like where I use time to wax philosophical about this stuff. I guess really a lot of the exercises in Vakil are kind of used to tie things together in like a way that is
Yeah.
gives the sort of geometric intuition. I like this is for me how I see math is very physical. Like I can't until I have like a physical like feeling, almost kind of like going
Yeah.
through a maze. Like I don't
Okay.
feel like I understand something. And so this is kind of like our intuition
Yeah.
for products is that it's like the pullback of Z through X and Y is the fibered product is all of the things that agree through the morphisms from
Right.
X and Y to Z.
Yeah, no, that last exercise really helped me understand fiber products. Like,
Yeah.
it was a big help.
So the theorem um fibered products in the category of topologies are intersections of open sets. Um, and so this is just thinking through our definition, right? Like, let's just set this up the same way. So X and Y are topological spaces that go into Z by alpha and beta. Then we have pi X and pi Y. This is not the fundamental group. I'm just going to clarify that now. And then we have the fibered product through Z of X and Y as the pullback. And so we know that this structure is the set of all things X comma Y in the product where alpha of X is equal to beta of Y. Well, X and Y are open sets in X and Y. And so the image of an open set isn't necessarily open, unless alpha and
Mhm.
beta are continuous, in which case, we do get this kind of thing out just by how we
Yeah.
set up morphisms of the category of topologies. And so because it's continuous, we're saying that the fibered product is where the images of open sets are the same.
Okay.
And so these are really intersections in Z um, of like sets which are or of open sets which are the same,
Yeah.
right? Um, and so this one proving this one is kind of like weird, but basically we
Really?
say okay, um, and I guess it's not intersections of open sets, but rather it's pre-images of intersections of open sets,
Okay.
right? Because we're maintaining the open sets which have the intersection,
Yeah.
right? So, and I would like to give, I don't have enough interesting topologies. Like the only way I can think of, I think it would be, I don't know, would it help you to give an example with three different topologies that gives us a fibered product?
Yeah.
Okay, then yeah, then we'll do it. Okay, so just as an example, um, let X be, I'm just gonna use metric topologies for X and Y, and then the quotient topology for Z, because that's just going to make all of this easier. Um, let X be R with the standard metric topology that we've used in real analysis. Let y be, maybe we want to pick a different topology. So I'm going to go ahead and pick out Z first, and I'm going to call it the power set of A, B, and C. Meaning that we have all of our singleton sets, we have pairs of each of the three, we have all three, and we have the empty set. So the power set is the easiest way to define a topology. It's actually called the discrete topology.
Okay.
And so what I'm going to say is we're going to define alpha, and we're going to define y in a second, but alpha of x in x basically takes on one of three things by natural injection. So if x is an open interval contained in, we'll say, maybe like -1 to 1. And I'm realizing I'm writing the piecewise function wrong. Then we're going to send it to A. And then we're going to send it to B if x is in the interval from, I guess, 1 inclusive to infinity, exclusive. And then C if x is in the interval from -infinity exclusive to -1 inclusive. And we can see that this clearly defines a nice way of looking at things, because we can take, maybe -1 in the open interval around this, and this gets chopped up into two separate open subsets, and then that becomes like the AB thing.
Okay.
Right? So we know that everything is well defined, and that this gives us a very nice surjection. And so then I'm going to pick for y, I'm going to pick a discrete set. And I'm going to actually, I'm going to call this, maybe like Z mod 10. No, let's do Z mod 11 with subspace topology from R. And I know that you aren't super familiar with topology, so I'm going to define all of this.
Okay.
So open sets in Y are, my iPad is losing power. Are sets where basically it's subsets of the power set of Z mod 11 intersected with open sets from R. So basically what this looks like are, I guess, okay, A intersect U such that A is a subset of Z mod 11 and U is open in R. So notably, what does this leave us with? This leaves us with the power set of Z mod 11.
Okay.
And so here we're going to define a more interesting projection, y down into Z, because we're sending the power set of 11 things, so 11 factorial things, into a set of 6 things. And so we can kind of create some interesting morphisms here. So B of y, we'll say is equal to A if maybe what's an interesting way we can define this? We'll say A if more than half of the points in y are even. And half of y is even. B if more than half of y is odd. And then C if 50-50. That's an interesting morphism right there, I think.
Yeah.
Right? And I'm not proving that these are morphisms, of course. You're taking me at face value here.
Yeah. I'll go
But
proof by
trusting,
intimidation for this.
yeah, trusting on good faith that these are in fact morphisms in the category of topologies, meaning that they are continuous maps. You know, since every set in the discrete, and here's my justification for it, I guess. So every set that we can get out of Z is open.
Yeah.
And so A of X gives us all of Z, all of the quotient topology. And then B or beta of Y gives us all the singleton sets in the quotient topology. And so we get that inverse images of open sets are always open. And yeah, that's just kind of going to work out nicely for us.
Yeah.
Yeah. So then basically the fibered product, because that's the thing that we're trying to compute here. So X product Y through Z is the set of Cartesian pairs of subsets of Z11. And I guess, oh, I forgot to actually put that this was basically the power set of Z11. But yeah, so subsets of the power set of Z11 and subsets of the real line with the standard topology, where basically we get singleton sets. So the only place where we get singleton sets are if we get exactly A, exactly B, and exactly C. Right? And so
Yeah.
we actually have a few specific cases for this. And so this is going to be a long thing to write out. This is a set, by the way.
Okay.
So all of the things where we get A is anywhere in Z11 where more than half of Y is even. And then in alpha of X, the only place where we get just A is if we have some open set in -1, 1.
Okay.
So the first half of our Cartesian pair is all open sets in R in, and then the second slot is going to be subsets of Z mod 11 where more than half is even. So this is going to be all of the stuff in the preimage of A. And then in the preimage of B, it's the same thing on the right-hand side, but in alpha of X, it's all of the open sets contained in the interval, in the ray interval from 1 to infinity. But of course, we can't include 1, and so it's all open sets. Sets in R in exclusive 1 to infinity. And then comma, subsets of Z, where more than half is odd. And then the part where we get C is that all open sets in R in negative infinity, again, to negative 1 exclusive. And then here it's going to be subsets of Z mod 11, where everything is 50-50. And then this is the fibered product of this in topologies. And we can see how this is basically the intersection of topologies in Z.
Yeah.
Like to be very clear here, we could not have gotten A and B in Z in our fibered product. So we get all of the intersections of the stuff in Z.
Yeah.
And rather we get the pre-images of the stuff in the intersections of Z.
Right.
So battery fast. So I think that maybe this is actually, I'm very glad that I did this example because this is a very helpful example for understanding fiber beams. Any questions you think that somebody watching would have?
Uh, Not that I know of. This is making a lot of sense.
That's good.
Yeah.
Okay, so our next thing, if Z is the final object in a category C and X and Y are objects in C, show that the fibered product is the same as the product. So again, if Z is the final object,
Yeah.
so theorem, if Z is final, and I can't really do a script C,
Hmm.
so I'm just gonna do a big C. And X and Y in obc show that the fibered product through Z of X and Y is the same thing as the product. Assume all relevant fibered products exist. And so, okay, breaking this down, Z is final means that Z has morphisms from every object in obc.
Yeah.
Has morphisms from every object in obc. And so basically what we have is the fibered product here but we also have a diagonal morphism. And then we also have this, and we have this thing here, phi, that we want to show as an isomorphism. And then the thing that is different about this diagram is that we actually do have a morphism from the product straight into Z. And so what we want to show is we want to show that this induced map in pink, which we're going to call psi. and then just labeling everything F1, F2, beta, alpha, pi x, pi y, and delta. And that is right, right? It's alpha on the bottom, yeah. So we want to show that basically phi is an isomorphism induced by psi. So I want to show phi is iso induced by psi. And actually maybe also delta. So we introduced a definition at the end of last lecture that kind of seemed unrelated, called a diagonal morphism. No,
Yeah.
this is not a diagonal morphism. Actually, I lied. I really wish he had given an example. This does look like it would be something you would call a diagonal morphism.
Yeah.
um, oh man, oh wow, okay. Battery is burning fast. And so basically, what we want to say is that um, assume phi is not an isomorphism, right? We can either do this constructively, um, which is going to be kind of a pain because we show that any any parent x product y goes through the fibered product, and we know that that's a unique factorization. So we know, if nothing else, right, phi factors uniquely. We've proved that. Um, and then we say, okay, this comes out to be x comma y in the preimage of z where alpha and beta are the same. And then we say, actually, let's do this constructively. I think constructive is going to work better. Okay. I love how I was trying to talk through how the constructive proof is. Oh, that's really funny. Okay. So let x naught comma y naught in x product y. Um, and then we know that and since the fibered product of x and y through z is equal to the set of all x and y in the product, such that alpha of x is equal to beta of y, and since psi of x comma y is in z, then basically all we have to do is say, okay, well, this is literally just pulling back the information from z. The product x naught comma, and I guess this should be x naught and y naught here. The product x naught comma y naught is in the fibered product. And then, so the conclusion of this is that the fibered product is contained in the product. Now we need to show the other direction, which is that the product is contained in the fibered product. No, we just showed that it's the other way around. We just showed that the product is contained in the fibered product. And the other conclusion of this is that n phi is injective. And then the other direction is, let x naught y naught in the fibered product then x naught comma y naught in X product Y has alpha of X is equal to beta of Y in Z. And then this is just the trivial containment, right?
Yeah.
So psi inverse of alpha X equals, equals psi inverse of beta of Y in the product. It has X naught comma Y naught and X comma Y. And so now the fiber product is contained in the product, implies set equality. And that's exactly what we wanted to show. Okay. Any questions about this?
Nope.
Technically, we should also show that phi induces an inverse, but they're the same set, and we map the same things to the same things, so it's an inclusion map, and so the inverse falls out as an inclusion map. Right. Hence, isomorphism. I think I'm okay with that.
Yeah.
Okay. Useful exercise. Towers of pullback diagrams are pullback diagrams. And so this is something that is useful because when we deal with homological algebra, we are going to deal with these things called exact sequences and then long exact sequences.
Okay.
And if we can show that something is a pullback, that gives us some nice properties. Okay, so theorem towers of pullback diagrams are pullback diagrams. What do I mean by this? Okay. U, V, W, X, Y, Z, looks like this. And if the two squares are Cartesian diagrams, show that the outside rectangle U, V, Y, and Z is Cartesian. So basically, what we're really saying here is replacing W with the fibered product through Z of Y, replacing U with the fibered product of V and Y through Z. Right? And I'm going to say, I'm going to now say that this is, to keep it consistent, U and nope, W.
Okay.
Oh. No, we want to show that this is the pullback of V. This is the pullback of W. And then we want to show that the pullback of W, and it's not through Z, it's through X. We want to show that the pullback through X with V. Wow, I wrote even that wrong. Holy. I did it a second time. There we go. Pullback through X of W with V is equal to the pullback of Y through Z with V. I'm just going to start by exchanging W. So we know that the pullback through Z with Y through X of V um and then this is where we induce the diagonal morphism. This is where the diagonal morphism becomes important. Is basically like we're so symbolically close. What we really want to do is we want to, I'm just going to copy and paste this. We want to find a way to cancel this piece out with this piece,
Okay.
or rather, just the X, and get this equal as Y through Z with V.
Okay.
And the way that we do that is, let me look at the definition of the diagonal morphism because I'm almost exactly sure that that's how we do this. The diagonal X is Y is a morphism fiber product through Y if the product of X exists. No, that's actually still not it. Um, hmm. Well, let's think about what this means. So the fibered product through Z with Y is the set of all pairs X and Y in the product XY, where, and now we need to start naming morphisms. I'm going to call this alpha, this beta. I'm going to call this theta and this gamma. And so then such that alpha of, oh, I hate that they switched places. Okay, hold on. I'm going to switch alpha and beta. So alpha of X is equal to beta of Y. But then what we have is that the pullback of X through Z with Y through X with V is the set of all pairs of W of wait, is it really? No, it's V. Yeah, W comma V in the product X pullback Y product V such that, and then this is where, yeah, so such that theta of W is equal to gamma of V. Well, what's theta of W? Theta of W is theta of pairs of XY. It's theta of pairs of XY.
It's pi x now.
No. Oh, that's such a great point. Oh, you hit that totally on the head, dude. Yes, it's absolutely pi x is equal to pi x of x comma y. Oh, that's so smart. So the pullback of x comma y is functionally y. So now we have the setup that like we're getting products in y
Yeah.
cross v, right?
Yeah.
So now we're set up with y cross v. All we need to show now is that this is through z, right?
Yeah.
And we already have that for free because um gamma goes as the composition of gamma and alpha,
Hmm.
right? So the
Yeah.
product of y through z with v is the set of all of the y's, which we're guaranteed to have, comma v's in y product v with beta of y equal to gamma alpha then gamma alpha circ gamma of v, but alpha circ but gamma of v is x. Gamma of v is x and x. Um, and so this is very clearly the set of this w and v, right?
Yeah.
So alpha gets us something in z.
Hmm.
Early yields containment. Does that make sense?
Yes.
Okay. I kind of hand waved a little at the end there. I think it's okay. I really
Yeah.
want to get to Yoneda's Lemma today.
All
So I'm
right.
going to speed this up a little bit. Um, yeah. Any questions you think that people will have watching this?
Um,
Probably a lot, but like,
yeah, probably a lot, but like
I feel like this is all pretty, like, I feel like
it's all
we're
straightforward.
not ready for it. Yeah.
Yeah.
Here's the thing that I like about category theory specifically is because really it's just a puzzle.
Yeah.
Like, honest to God, it just feels like I play video games all day because it's like I'm just doing puzzles. It's like, I mean, I don't
Yeah.
get paid very much to be basically a professional Sudoku player here, but like,
Right.
theoretically, right?
Yeah.
Okay. So, um, there are natural morphisms between fibered products. I'm gonna state this as a theorem because the exercise is to figure out the diagram. So
Go.
we're given morphisms x1 into y, x2 into y, and then y into z. Show that there is a natural morphism through the fibered product of y of x1 with x2 into the fibered product of z. So hold on. Oh, this is going to take a second. So fibered product through y Oh, this is notational hell. Um, and then through the Cartesian. Oh yeah, with Z. Oh yeah, this is really trivial. Um, and then the thing that we're proving exists. Is the phi here is an isomorphism?
Mm-hmm.
Or no, it's just a morphism. It's a natural morphism. And then just as kind of dotted line arrows, those things exist. And I'm just gonna say that phi exists, and it's pretty obvious why.
Yeah.
Um, okay, important exercise. The diagonal base change diagram. um, yeah. So theorem base change diagram. So suppose we were given morphisms x1 and x2 into y and y into z. X2, y, y into z. And then we have a Cartesian square where we have the fiber product of x1 through y with x2. And then we have the z product of x1 and x2. Oh, wait, hold on. This is just a copy of the above. Hold on. But then we add one thing. Um, so we have the Cartesian product through y and through z. We have a diagonal morphism. I'm adding all the new things in pink.
Okay.
Um, we have a morphism from this into y, and then we have the fibered product, the diagonal morphism of y through z with y. This is the diagonal thing.
Mm-hmm.
And then that goes into z. Yeah, that has to go into z. Yeah. And so then we want to show that if this is our setup, then wow, that is hell. Um, x1 fiber product x2 through z with y, and then here's the weird part that we're not used to: the diagonal product is a pullback diagram, meaning that the pullback of x1 and x2 through y is the pullback of the diagonal morphism of
Mm-hmm.
y across y. Okay, so let's start labeling things. Okay, Oh God. Oh fucking hell. What is this? Okay. Morphisms are in orange. Alpha, beta, pi x2, pi x1. Um, delta y, but lowercase delta y, not to be confused
Hmm.
with capital delta. F1, F2, y to z we'll call theta. And then we need gamma here. I don't think we need these. Nope, we need those. Damn it. um, I'm running out of Greek letters.
Psi.
Psi, we haven't used psi yet. Okay, and psi prime. So then the morphism of the fiber product of xy through x2 to xzx2 is phi inverse. And then, and notably, it's actually not phi inverse. So I lied. It's gonna be what could it be?
What's
Another
that?
letter. Bait.
Lambda.
We're going. Oh, lambda. Yeah, that's easy. Okay. Okay. So y to z is lambda. This thing to y. Oh, we needed one more morphism.
Mu.
Mu. Mu y into its diagonal morphism was delta y, and then the fiber product of z into the diagonal morphism. Come on, there's got to be another letter.
Algebraic.
Delta.
Zeta.
I can't draw that.
Like a weird
My
squiggle.
handwriting's hard enough to follow as is.
Kappa.
Um. Okay, I'm going to the Hebrew alphabet because that's my last ditch effort. Okay, so now let's write out all of the things that these morphisms are
Oh, you
equivalent
forgot
to.
sigma.
Oh, I did forget sigma. Okay, no need for Hebrew alphabet just yet. I'm
Yes.
sure we will hit a point. God, if this isn't you really you thought that one diagram with Galois theory was bad over the summer.
This is bad.
Oh my goodness, this is a new. I'm taking a picture of this actually. This is for posterity.
Yeah, throw this on
Um,
your LinkedIn. Show them what you've been having to write.
yeah.
If anything, you know your Greek alphabet.
I don't know. I had to ask for help. So, um, let's start by writing out all of the things that our function compositions can be. So sigma has to go through delta y. So delta y is the last thing to go. Or is it the first thing? No, it's the last thing. So sigma starts with delta y, and then now we have 1, 2, 3, 4, 5 paths that this could take.
Hmm.
You will appreciate how useful this diagram is when you repeatedly use the diagonal morphism in proofs and construction. What? Okay, let's just think through intuition here before we start trying to formalize everything. What do we want to show? We want to show that x1 fibered products through y x2 um is the same set as the fibered product of y and xz with x2. Hold on. Let me write this down. There's too many symbols. This is entirely
Yeah.
just here. When I title this lecture on YouTube, I'm just gonna call this the base change diagram of doom. Okay, so what do we want to show? We want to show that um, that x1 fibered products through y x2 is the same set as the fibered product y through the diagonal um, diagonal morphism with x1 fibered products through z x2. So on the face of it, and let me make this smaller so it's clear that that is a Cartesian product.
Yeah.
On the face of it, this kind of makes sense.
Yeah.
So now all we got to do is we just got to plop something in the left-hand side, and then plop something in the right hand, and then show it's in the right-hand side, plop something in the right-hand side, show it's in the left-hand side. Um, Holy diagram of doom. That is evil. That is like
Yeah.
evil. Um, oh my goodness. Okay. I mean, I think that like no, it's okay. No, we can't bump this to exercise. We just got to do it.
Yeah.
Okay. So let x1, x2 in the fibered product of y to x1 and x2. Then okay, what is it that we know? So x1 and x2 are in the product. I'm not even gonna write it in. There's a product of x1 and x2 in here somewhere floating around.
Yeah, it's right there. It's what
No,
line
no,
is
just a
it in?
regular product. Um, but basically these are things which process nicely through alpha and beta. So then alpha of x1 is equal to beta of x2. And now we want to define the set notation of y fibered product y fibered product z diagonal y x1 fibered product z x2. What what a life, man. You know, like the one Popeyes strip
Yeah.
where he's like, what a life. If you're 21.
Um,
We're not even 21.
not yet.
Okay. Oh God. Okay. And my iPad is dying. There's time pressure. So this is equal to the set of y comma x prime 1, x prime 2 in y product, fibered product through z of x1 and x2 such that delta y and sigma factor nicely. So delta y of y is equal to sigma of x1 fibered product through xz, x2. So we want to be able to write x2 and we need to look at lambda and mu again. Where's lambda? Where is the chain? Okay, hold on. I'm
Oh,
gonna take out
lambda
a
is
highlight.
the x1 fiber product through y x2 back to the fiber product through
So
x2.
x1 through y is lambda. And then lambda factors through sigma. And then mu goes diagonally. And then y goes through its diagonal morphism. Okay, I'm happy with this. This is making sense
Yeah.
now. And so we need to show okay, so what we're showing here, alpha of x1 and beta of x2 live in y. These live in y.
Yeah.
And so then we're saying that since they live in y and since delta y goes into the fibered product of the diagonal morphism, that this Garrett,
Yeah.
where? Oh, there's z. Okay, I was about to crash out. I couldn't find z. And that basically, okay, if we have, I was like, if we've been trying to prove something that doesn't exist. So if we have alpha of x1, beta of x2, and these get sent through delta y, that is the diagonal fiber product of z, and we're given that that exists.
Okay.
So we know that x1 and x2 live in y diagonal morphism through z. But then the diagonal morphism of y through z. Oh, so we get containment. We get containment. That's fine. Because we can construct that this y is that alpha of x1 equals beta of x2 is y comma something in this. And so now we just need to find the thing that is equivalent to it through what morphism is this equal to? So we have that the product of y with itself through z is all of the things in the product of y where theta of y1 is equal to gamma of y2. So want theta of y to be equal to gamma, I think that's right. Yeah, gamma of the thing that feeds of delta y of x1 prime, x2 prime. But then x1 prime and x2 prime are the preimage are the preimage of y in y. So we get forward containment. Does that make sense? So we're saying we get the same thing in here by going back this way or going back this way, and then up to x1 and x2 prime. Does that make sense how we get the forward containment?
Could you repeat that? I'm sorry, my dad came in.
Oh, no worries. So basically, x1 prime and x2 prime are the preimage of y and y through the fibered product back here.
Okay.
And so we pick our thing in z and we trace it back like this, and we get the same thing.
Okay. That makes sense.
So we get the forward containment. And then this means that this is not equal yet, but it is contained. And now we want to put something in y cross the fibered product of the diagonal morphism with x1 fibered product x2 and show that it is in the fibered product of x1 and x2 with y. And this direction is kind of trivial. because what we're doing is we're making a loop. I'm going to do this in red, and I'm going to do it in chunky red. We're making a loop like this and a loop like this, and then tracing it back through this diagonal, or through that Cartesian square. That one, this is actually the easy side. We just did the hard side. Oops, no. Okay, goodness. This is, oh my Jesus. Now we want to show the opposite. So let y comma x1 x2 in this thing then we know that gamma and theta of this thing are equal. So then gamma of y is equal. Wait, I think it was the other way. Yeah, it was the other way. Then theta of y is equal to gamma of x1 comma x2. And then basically, but gamma of x1 x2 is equal to delta y of y. And then this exactly yields. So the preimage of y and y is x1 comma x2 and x1 cross x2 such that alpha and beta alpha of x1 equals alpha x2, and so we get the reverse containment. That was actually way easier. That was so much easier. And we get set equality. Okay, maybe easy is not the word we're looking for here, but like, come on.
No.
Okay. So we did the base change diagram.
All right.
That was a tough problem. That was some like
Yeah.
goodness gracious. I'm kind of proud of that. That like
Yeah.
that was some real cojones.
Yeah.
Okay. So breaking things in easy with the definition. So a coproduct is a product in COP, or rather a coproduct in C. And then a fibered coproduct in C is a fibered product in COP.
Could you go
So
over
what
what
is
COP is again?
COP is C, but the arrows are reversed.
Okay.
So remember we defined a product by this unique factorization where we got x and y and f1 and f2.
Yeah.
And we got unique factorization there. So if this is in C, then in C op, it's going to look the same, except the arrows are going to be switched.
Okay. That makes sense. Thank you.
And then a fibered coproduct is defined by the diagram x through zy, y, x. Z with a unique factorization.
Yeah.
But then in C op, we're just gonna erase the arrows in reverse. And then coproducts are denoted by an upside down pi.
Okay.
6%. Theorem coproducts in the category of sets are disjoint unions. So in the category of sets, morphisms between sets are just functions. And so what we're doing is we're taking stuff from X and Y, which are two different sets, factoring them through their product, and then looking at what is unique through them. And so, yeah, that has to be disjoint sets.
Yeah.
Oh, God. Okay. So the theorem, this looks like another long one. So we're looking at ring morphisms between A modules with tensor products. Okay. This is the last exercise before we can really get to the Yoneda lemma. Maybe we'll just state the theorem and I'll make it homework.
All right.
Between now and tomorrow. So, okay. Then in this case, theorem, if we have A to B and A to C. So A, B, C are ring morphisms. And B and C are A modules. Are A modules. With B tensor product A, C has ring structure. We want to show that there is a natural morphism which gives a fibered coproduct on rings. With, oh, I did this the other way. No. With B, AC, then B tensor product AC is the fibered product through A and C. So yeah, this is homework. My iPad's about to die. Real quick, a monomorphism is kind of a, and I guess I'll just end with these definitions so that we can just start with the Yoneda lemma. So pi from x to y is a monomorphism. Monomorphism. If pi circ mu1 equals pi circ mu2 implies mu1 is equal to mu2. And then an epimorphism is the left-hand side of this. Is
what
the
morphism?
an epimorphism is the dual of this. So it's so the diagram for this is if you have Z into X, which goes into Y by pi. Then basically there is less than or equal to one way to get from Z into X.
Okay.
But then an epimorphism is the dual. Pi is an epimorphism. If it is the error reversing of this. Yeah. So basically, this is the analog of injectivity and surjectivity.
Okay.
Um, And actually, because I'm holding steady at 5% battery, I think I'm going to end this with Yoneda's lemma, with stating Yoneda's lemma. Because this gets us up to limits and colimits. So actually, don't do this theorem unless you feel like it, like if you don't feel comfortable with tensor products.
Okay.
But yeah, Yoneda's lemma, since we have 20 minutes. Okay, I'm just going to read his preamble. Much of our discussion about universal properties can be cleanly expressed in terms of representable functors under the rubric of Yoneda's lemma. Yoneda's lemma is an easy fact stated in a very complicated way. Informally speaking, you can essentially recover an object in a category by knowing the maps into it. For example, we have seen that the data of maps to the product of x and y are canonically the data of maps of to x and y. And so now we have taken this as the definition of x product y. So Yoneda's lemma says that you can recover objects in a category by knowing the maps into them. And so this is kind of our notion of universal properties, right? Like if we set up a diagram that is a Cartesian square, like a pullback diagram, we now know everything about pullbacks. And so we never have to question anything about the object. We just know that there's a functor to some category that like makes it easier to solve the problem that we're trying to do. And so basically, more formally, let A in ob C then there exists a set of morphisms. Oh, sorry. Let A and lowercase c there exists a set of morphisms between C and A. If F is a morphism from B to C in morphisms from B to C, then we get a map of sets, morphisms C comma A to morphisms from B to A by composition. By composition, we and basically the idea is that we can pre-compose with F.
Yeah.
This yields a contravariant functor HA from the category C into sets. And I'm just going to clarify with obc that this is the same script C. And then Yoneda's lemma says that HA determines A uniquely up to unique isomorphism.
Yep.
So HA determines A uniquely up to unique isomorphism. And so what this means is that we can take something, like if HA is a forgetful functor from the category C to the category of sets,
Yeah.
then taking its contravariant from sets back to C determines the structure of an object from a preimage of a set.
Yeah.
So I'm going to instead make the homework 1.2y in
Okay.
so 1.2.y, and this is what we'll open up with next time, is basically proving this more rigorously, kind of as a step-by-step thing. And then 1.2z is what we'll talk about. And we will open. Whoa, that's not a word. Open with 1.2z tomorrow.
Okay.
And by z 1.2z c. And so there's a joke at the end of this section that made me laugh my head off when I read this for the first time. I was with my in-laws, getting ready to go to Princeton for my visit, and
Yeah.
I was reading through the Yoneda Lemma just to brush up on category theory because there was a paper. Let me go ahead and turn my iPad off. There was a paper that I was preparing for that was being presented at the seminar that I was going for. And basically it was had to deal with some category theory. This joke made me laugh for no less than 30 minutes straight. And they just kept asking, and the funny part ended up being that they kept asking me, "Oh, well, what's so
Yeah.
funny?" And I kept saying, I can't possibly explain this to you in a short period of time. But yeah, the Yoda embedding. Contravariant it is.
That's great.
Okay. So thank you for tuning in, time and attention. Today was definitely a tough day. Next time we will finish the Yoneda lemma, talk about limits and co-limits, and I will be hoping to get us up to adjoints. And then the following time we will talk about adjoints.
Yeah.
And then we'll get to abelian categories the time after that. And then we get into homology and simplicial complexes.
All right.
So, all right. Turning the recording off. Thank you. Have a good day.